Good. A very warm welcome to all on this channel. I am Dhananjay Kumar Raman, Assistant Professor in Mechanical Engineering Department, IIMT College of Engineering, Greater Noida. In this session, I am going to tell you about a very interesting topic, theories of failure. And this theories of failure, which is comes in the subject strength of material. That means when we are going to design any component, then at that time, or we are talking about the strength of the material. And to design the component, we can choose the strength and we can choose the different types of theories of failure to find out the dimensions of the component. But before going to understand these theories of failure, first of all, we should understand what exactly the failure means. As I can show you in the next slide, failure means what? In this session, we are talking about the mechanical component, and in this mechanical component that are applicable in different types of applications, in different types of machines, in which different types of parts or elements can be used, and there are different types of forces which are acting on the machines, and because of that type of forces the stress is induced in the component. And when the stress is induced in the component, if material cannot sustain the maximum limit, then the component may get fail. So first of all, we should understand we are talking about the strength basis. That means when we are going to design a component, then we are talking about the strength if you are taking this theories of failure. So as you can see, these theories of failure, first of all, we should understand why we need these theories of failure. Since we know that in ideal conditions, we can apply if load in uniaxial direction, then there is only one direction load application. And because of that load, if we are going to increase that load, at some point our material or component may get fail or may get deformed. So fail means not only fracture, it may get deform also. That means plastic deformation occurs or permanent deformation occurs on the material. If you are talking about the brittle material, if you are talking about the ductile material, both materials are different in nature and both materials can fracture in different ways, can fail in different ways. So for the sake of convenience, first of all, we should do the test on the material and to find out the different values, different properties of the material on strength basis. What is that test? We can perform a test on ultimate tensile testing machine, that is UTM machine, with the use of standard specimen, and that specimen is made of that material which we are going to use in the design of component. So after doing the test, after the completing the test, we can draw the stress strain diagram. As you can see in this stress strain diagram, after the application of load, strain can be drawn on x-axis, and accordingly the stress can be drawn on the y-axis. If we apply the load, then the material opposes that external load application. That means strain is going to happen, and because of that strain, stress is going to increase. That means our material is going to oppose the external application of the forces. So when load is going to increase, strain and stress is going to increase up to some point. As you can see in this slide, the curve is straight line, but after some point we can get the value of yield strength, and then is this curve is going to deviate. That means now it is not in straight line, and at the maximum point we can get the value of ultimate strength of the material, and ultimately our material will get fail if we are going to again increasing the load of the component. So, and this test performance is the application of only one load in uniaxial direction. And because of that test performance in simple tensile test, we can draw this stress strain diagram, and from with the help of this diagram we can get the properties of the material, that means strength of the material, yield strength of the material, and ultimate tensile strength of the material, since these two strengths are very important for the design of any component. Yield strength we are considering if we are talking about the ductile material, and ultimate strength we are considering if we are talking about the brittle material. And up to the yield point, the curve is straight. That means after the removal of the load, our component, there is no any permanent deformation occurs in the component. That means our material is safe, or we can say our component is safe. But after this straight line, there is a plastic deformation, and because of that plastic deformation, the permanent deformation occurs. That means after the removal of load, that material would not get its original position. That means whatever the component is, that is of no use. That means it would not give you the satisfactory result. So these theories of failure, why we need these theories of failure? In real practice, whatever the component, whatever the element we are going to use in the machine part, at the time of running, there are different types of load acting on the component at different directions. So at different directions, the different direction stresses are also induced on the component. So it is very difficult to predict because of which stress or because of which forces our component is going to fail. That is why this theory of failure comes into the existence. And then there are different scientists who gave these theories of failure. Now come to this topic, theories of failure. So there are different types of theories of failure. There are different scientists who gave the theories of failure, and these theories also known as their scientist name also, in which the first one is maximum principal stress theory. This theory is also known as Rankine theory. Second theory is maximum shear stress theory. This theory is also known as Coulomb-Tresca and gauge theory. Third theory is maximum principal strain theory. This is also known as Saint-Venant theory. Fourth theory is total strain energy theory, and this theory is known as Hicks theory. And the last theory, fifth one is distortion energy theory, and this theory is known as von Mises and Henke's theory. Now let us discuss one by one of these 5 theories of failure. If we are talking, so before going to start these theories of failure, first of all we have to take the material and made a standard specimen and perform a test on the UTM machine and find the properties of the material, that means yield strength of the material and ultimate tensile strength of the material. So if you're talking about maximum principal stress theory, and there are maybe whatever the material we are going to use for the machines, the forces may be in uniaxial direction, the forces may be in a two-dimensional stress system, the forces may be in three-dimensional system. So whatever the systems there are, we can calculate the principal stresses of the component of the material, that sigma 1 and sigma 2. These are the two principal stresses, and these two principal stresses are mutually perpendicular to each other. So first of all, we should understand what is the statement of these theories. According to these theories, the failure of a mechanical component subjected to biaxial or triaxial stress system occurs when the maximum principal stress at any point in the component becomes equal to the maximum principal stress when we are going to perform a simple tensile test for that material, that particular material. Then what happened? Whatever the forces applied on that component, we have to calculate first principal stresses of the material. Let us suppose sigma 1 and sigma 2, these two are the principal stresses which are two dimensional in which are perpendicular to each other, and take one case, first case, suppose sigma 1 is greater than sigma 2 or sigma 2 is greater than sigma 2. So if you are going to apply these theories of failure, then if we are going to increase the value of the forces, because of that forces, if we are going to increase value of forces, the sigma 1 stress is also going to increase and sigma 2 is also going to increase. So when sigma 1 is greater than sigma 2, then after the increasing of the load, sigma 1 is going to reaches up to the yield point of the stress. If then our component may get fail. Here you can see that the equation sigma 1 is equal to plus or minus. There are two signs, and in sigma yt is the yield strength of that particular material. That means this is the properties of material, and this is the constant value of that particular material. That means if sigma 1 is greater than, so for sigma 1 reaches to sigma yt, and positive signs we can take if the stress is positive, negative sign if we take stress is negative. So from here we can find out these two equations. If sigma 2 is greater than sigma 1, then after increasing the load, this sigma 2 is going to reaches to the sigma yt, up to the sigma yt. Then our component will get fail. Similarly, positive sign is for tensile stress and negative sign is used for compressive stress. These are used for when we are taking the ductile material, and if we are using the brittle material, then on the place of yield strength we can use ultimate tensile strength of material, because we cannot get the yield strength on stress strain diagram. So in this, again we can say that if sigma 1 is greater than sigma 2, then sigma 1 maybe reaches to sigma ut after the increasing load, and positive and negative signs are according to tensile stress or according to compressive stress. Similarly, if sigma 2 is greater than sigma 1, then after the increasing load, sigma 2 going to reaches to the ultimate tensile strength of the material, and positive is for tensile load and negative is for compressive load. So here, if you are talking about the ductile material, then you can see there are four equations. One is sigma 1 is equal to plus sigma yt. Second one is sigma 1 is equal to minus sigma yt. And if sigma 2 is greater than sigma 1, then sigma 2 is equal to plus sigma y2, and sigma 2 is equal to minus sigma y2. So these are the four equations. And with the use of these four equations, we can get the region of safety. So since we know that sigma 1, sigma 2, these two are the principal stresses, and these two are mutually perpendicular to each other. So we can draw on diagram sigma 1 is on x-axis and sigma 2 is perpendicular to sigma 1, so sigma 2 is on y-axis. since sigma yt is constant value for that particular material, so sigma 1 and sigma 2 are variables because it depends on the value of the application of the forces. If forces is decreased, sigma 1 or sigma 2 is going to decrease. If forces are increased, sigma 1 and sigma 2 are going to increase. So by taking these four equations, and these four equations can represent the equation of straight line. So this equation of straight line can be draw here. One is this one, another one is this one, and one is this one, and one is this one, according to positive and negative sign of the equations. So the area which is bounded by these four straight lines are the safe region of the component. That means if the value of the stresses which are acting on the component lies in between these bounded curve, then our component is safe. That means we can use that component. If the value of sigma 1 or sigma 2 falls below this region, that means out of this regions, then our component may get failed. That means may get fractured, or that means may get permanently deformed. If material is going to get permanently deformed, then that material will not, that component will not give the satisfactory results. So this is the maximum principle stress theory. Now next theory is maximum shear stress theory. As earlier we told you about the second name of another name of this maximum shear stress theory is Coulomb, Tresca and Gauge theories. So first of all we should understand what is the statement of this theory. According to this theory, the failure of any mechanical component, if that are subjected to maybe biaxial stress system, maybe triaxial stress system, maybe uniaxial stress system, when the maximum shear stress at any point of the point in the component becomes equal to the maximum shear stress in standard specimen in simple tensile test. That means we are considering the uh, we are considering the you can say same material. That means whatever the component material of the component, we are going to make the standard specimen of same material and perform the test and get the value of their properties. So according to this theories, if there are different types of forces are applied on the component, then first of all we can get the value of we can find out the value of principal stresses. That means sigma 1, sigma 2 and sigma 3. And these, since these are the principal stresses and these three principal stresses are individually perpendicular to each other. So if you are talking about three-dimensional stress system, then here we are talking about the shear stress. So we are considering maximum shear stress. From the formula, we can take tau maximum, maybe sigma 1 minus sigma 2 by 2, or maybe sigma 2 minus sigma 3 by 2, or maybe sigma 3 minus sigma 1 by 2. Any one of them is maximum, can correlate to the maximum value of the standard test specimen when material gets failed, and at that time what would be the maximum value of shear stress. If you are talking about the biaxial shear stress system, then tau maximum, here what we are doing, here we are doing the third stress, that is sigma 3 would be considered as 0. So there is only two stresses, sigma 1 and sigma 2. So put the value of sigma 3 is here 0. So tau maximum maybe sigma 1 minus sigma 2 by 2, or sigma 2 by 2, or sigma 1 by 2. If we are considering uniaxial shear stresses, then this tau maximum is sigma 1 by 2. Now, at the time of failure, as we know that in simple tensile test that there is load application is gradual and in one direction. So there is uniaxial loading. At the time of failure, sigma 1 would be reaches to sigma yt. So tau maximum would be reaches to sigma yt by 2. This is the maximum value of shear stress when uniaxial loading occurred on the component. So for the safe reason, for three-dimensional stress system, we are unable to draw the diagram on this 2D plane. So for two-dimensional stress, we can consider. Now, if we are applying that theories of failure for triaxial stress system, this sigma 1 minus sigma 2 by 2 is equal to plus or minus sigma yt by 2, 2 by 2, 2 and 2 cancel. Then this equation comes sigma 1 minus sigma 2 is equal to plus or minus sigma y by 2, sigma yt, where positive is considered for tensile stress and negative is considered for shear stress, compressive stress. Similarly, if sigma 2 by 2 minus sigma 3 by 2 is maximum, so sigma 2 minus sigma 3 is equal to plus or minus sigma yt. Similarly, sigma 3 minus sigma 1 is equal to plus or minus sigma yt. So these six conditions, these six equations, by the use of these six equations, which one is greater, we can calculate the value of the dimensions of the component. If we are considering two-dimensional stress system, so for biaxial stress system, maximum shear stress sigma 1 minus sigma 2 by 2 is equal to plus or minus sigma yt by 2. 2 cancel. So this equation would come sigma 1 minus sigma 2 is equal to plus or minus sigma yt. And sigma 2 is equal to plus or minus sigma y2. And sigma 1 is equal to plus or minus sigma yt. As you can see in the previous slide, these are the sigma 1 minus sigma 2 by 2 or sigma 2 by 2 or sigma 1 by 2. These are the value of the shear stresses. Which one is greater? We can compare it with the maximum value of the shear stress in simple tensile test. So from these six equations, sigma 1, sigma 2 is equal to plus minus, sigma 2 is equal to plus minus sigma yt, sigma 1 is equal to plus minus sigma y2. So here we can get these six equations, and in these six equations we can see that sigma yt is the properties of the material, this is the constant value, and sigma 1 and sigma 2 are the variables of the component. So these six equations also represent the equation of a straight line, and if we draw it on x and y axis by considering on x axis sigma 1 and by considering on y axis sigma 2, so these six straight line can be represented like this, and the region which is bounded by all these six straight line is the safe region. That means if the value of any species that falls that lies in between these bounded area, then our component is safe. And if that value is lies means out of this region, then our component may get failed. That means there may be a chances of plastic deformation, there may be a chances of fracture. Now next theory is maximum strain energy, maximum strain theory. So if you are talking, since the other name of this theory is Sen-Venance theory, so first of all we should understand what the statement of this theory. The statement is yielding at a point in the material begins when the maximum strain corresponding to complex state of stress. That means that state of stress may be three-dimensional, that state of stress may be two-dimensional, that state of stress may be uniaxial. So whatever the maximum strain corresponding to the whatever the state of stress, if it exceeds the maximum strain corresponding to yield point in simple tensile test, that means at the time of the performance of test on simple tensile test for that particular material, at the time of failure, what is the maximum strain that has to be that means noted down, and whatever the maximum strain in real condition, that is to be compared with that values. So if you are applying these theories, then whatever the forces we have to calculate the principal stresses of that material, that means sigma 1, sigma 2, and sigma 3. These are three principal stresses which are mutually perpendicular to each other. And if you are applying this theory for shear, that is strain, then the value of strain is for triaxial system is sigma 1 minus mu is Poisson's ratio. That means sigma 1 minus mu into sigma 2 is equal to plus or minus sigma yt. That means plus is for tensile and minus is for compressive stress, and mu is Poisson's ratio. Similarly, if sigma 2 minus mu sigma 3 is equal to plus or minus sigma yt, or sigma 3 minus mu sigma 1 is equal to plus or minus sigma yt. So from these six equations, if the spaces in three-dimensional in condition, then with the help of any one of these six equations which is satisfied, that can be used to find out the dimensions of the component. And if we are talking about the biaxial stress system, then sigma 1 minus mu sigma 2 is equal to plus or minus sigma yt, and sigma 2 minus mu sigma 1 is equal to plus or minus sigma yt, as we are considering sigma 3 is 0. That means there is no third principal stresses. So from these four equations, you can see here for biaxial stress system, again we can draw the safe region in the diagram, since sigma 1 and sigma 2 are the principal stresses, and these are the variables, and mu is the constant value. This is the Poisson's ratio, and this is the properties of the material. So it is a constant value, and sigma yt is also a property of the material. So this is also constant value, and positive or negative signs represent the if the stress is in tensile in nature, or negative when we are if we can consider negative if stresses are compressive in nature. So with the help of these four equations, we can draw the safe region. So in this four equation, we can also see that mu is a constant value, sigma yt is a constant value, and sigma 1 and sigma 2 are the variables, and x-axis represent the sigma 1 value and y-axis represent the sigma 2 value. And by putting different values of sigma 1, we can get the value of sigma 2, or value of sigma 2, we can get the value of sigma 1. So we can find the straight line like this, and whatever the area or region that is bounded by all these four equations, four straight line equations, that region will give the safe region. That means whatever the stresses are induced in the component, that means our component is safe. And if the value of that stresses falls below that region, then our component may get fail. Now, next one is total strain energy theory. In total strain energy theory, the other name of this strain energy theory is Higgs theory. Higgs is the name of scientist. So, according to this theory, the yielding at a point in a material begins only when the energy per unit volume absorbed at a point is equal to the energy under uniaxial state of stress, as in case of simple tensile test. Now again, we can say that whatever the forces applied on the component, first of all, we would have to calculate the value of principal stresses sigma 1, sigma 2, sigma 3, which are perpendicular to each other. And for triaxial stress system, we can write the equations sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 into Poisson's ratio into in bracket sigma 1 sigma 2 in plus sigma 2 sigma 3 plus sigma 3 sigma 1 is equal to sigma yt square. So with the use of this equation, we can get the value of dimensions of the component. And if you are talking about the biaxial stress system, then the equation would comes like this: sigma 1 square plus sigma 2 square minus 2 into mu sigma 1 sigma 2 is equal to sigma yt square. If you are seeing these equations, then in this equation sigma 1 and sigma 2 are the variables. That means if you are going to increase the value of the load, then sigma 1 is going to increase or sigma 2 is going to increase or accordingly decreases. And mu is the Poisson's ratio, that means it is a constant value, and sigma yt is a constant value since this is the properties of material. So this equation would represent the equation of ellipse, and by putting uh, different values of sigma 1 we can get the value of sigma 2, or different values of sigma 2 we can get the value of sigma 1. So so by locating all these points, we can get the safe region. That means whatever the stress is, that if that lies in between this region, then our component is safe. And if that value uh, falls outside this region, then our component get failed. Now the last theory is distortion energy theory. If you're talking about this theory states that the yielding at a point in a material begins only when the strain energy of distortion per unit volume at any point in the component becomes equal to the strain energy of distortion per unit volume in simple tensile test. And same thing applied on this theories also. Whatever the forces, application of forces in the component, first of all we would find out the value of the principal stresses sigma 1, sigma 2 and sigma 3, which are perpendicular to each other. And if we are putting all these value in the equation, that means to find out the distortion energy, so the equation for triaxial stress system would comes like this: sigma 1 minus sigma 2 to the whole square plus sigma 2 minus sigma 3 to the whole square plus sigma 3 minus sigma 1 to the whole square is equal to 2 sigma yt square. So with the use of these equations, we can get the dimensions of the component, or we can say we can design the component. And for biaxial stress system, the this equation would comes like this: sigma 1 square plus sigma 2 square, as you can see here, minus sigma 1 sigma 2 is equal to sigma yt square. Here we can see that sigma yt square, sigma yt is the constant value, so and sigma 1 and sigma 2 are the variables. So once again this equation would represent the equation of ellipse. So by putting one value we can get the another value, and by doing so we can find out the safe region. As you can see, this green region, this is the equation of this ellipse, and this region represent the safe region of the component. That means whatever the stress is, if that lies in this region, then our component is safe, otherwise that component may get failed. So this is all about the theories of failure, and by doing so, whatever the forces, application of forces acting on the component, first of all we would find out the principal stresses of the value of the component. We can find out the maximum stresses of the component. We can find out the maximum strain of the component. We can find out the maximum total strain energy of the component, and we can find out the distortion energy of the component per unit volume, and compare it with the simple tensile test performance values. And by comparing we can get the dimensions, we can design the component dimensions of the component. Thank you.